Hello, everybody. So, in this chapter, or this section, we're talking about how stationary states affect us. Well, first of all, we have to start introducing our wave equation, which is going to be equals to I h bar, and then the derivative of our psi, capital Psi, remember that, over dt is equals to negative h bar squared over 2m, and then the second derivative of our psi, capital Psi, in terms of x squared plus v, capital Psi. So what we want to do is, since we know that psi, capital Psi, is in terms of x and t, we can use separation of variables, which is naturally always going to use as a physicist, and do this. So let's say that we have a function that is just in terms of x, and another function that is just in terms of time. Okay, so we can just take it and plug it in our initial equation. So IH bar, and then the derivative of, instead of this capital psi, we write small psi in terms of x, and then phi t, and derive in terms of t is equals to negative h bar squared over 2m, and then the second derivative of our psi in terms of x, phi in terms of t, in terms of x, plus v in terms of v, the multiplied psi in terms of x, and phi in terms of t. Okay. Now, one thing we can do is that we can divide both sides by our capital Psi. Actually, sorry. I'm gonna do one step before that, and I'm gonna say on the left side we have I h bar, and then the first part over here, we can see it's just in terms of x, so just constant. We can take it out, and we're gonna have psi x, and then the derivative are phi t over, in terms of t, sorry, is equals to negative h bar squared over 2m, and then the second derivative of this. But again, this one, we said this part is just in terms of t, so it's just a constant, so we can take it out. We're gonna have phi t times the second derivative of our psi in terms of x, little psi, not capital, in terms of x squared, plus, and here we'll just say that it's gonna be v psi, capital psi, and then phi t. One thing that I want you to pay attention to is the fact that our potential will be independent of our time. That's what we say. So this one is just going to be equals to 1. Okay, and now we can divide both sides by our capital Psi. So we get I h bar times, well, we get rid of our little psi, and we get over phi t, then derivative of psi in terms of t, is equals to negative h squared over 2m, and then psi, actually we divide by capital Psi over here. Remember, it's going to be equals to, as we said at the beginning, this part over here, and so we get 1 over little psi in terms of x, second derivative of our little psi in terms of x, okay, plus, well, we divide it here, we get simply our, actually sorry, here we would simplify our time and everything, so we'll just get b. Okay, so what do we know? Well, as we can see now, the left side is just in terms of t. There's no x anymore. So this one in terms of t, and the right side instead is gonna be in terms of x. that means that if we change time, then we don't change x. Our value on the left has to not change, because if we're to change on the left side by changing the time, we're not changing the right side. And we say that these two things are the same. So it means that if we don't change the right side, we don't change the left side. So if we only change the time, we're actually not changing anything. So we can say that the left side, actually, let's see, the right side is going to be a constant. Let's call it E for right now. So we can say now that this phi h bar over phi hat, phi in terms of t, derivative of phi in terms of t in terms of t, is equals to E, right? Okay, so now why don't we solve this? We multiply both sides by dt, and we moved the numerator over here on the left side. So we get derivative of phi t over phi t. Oops. And we're integrating, of course. And we're going to get negative I e over h, because remember that 1 over I is equals to negative I. You can prove it the long way, I don't feel like doing it right now. And then dt. So if we integrate the left side, we're going to get ln of phi t is equals to negative I e t over h bar. So, we can put everything to the power of e. So we get, here we get a c, but we don't care about the constant. We get constant of integration right now. So we just avoid it. And so we get phi t is equals to e to the power of negative I e t over h bar. So we find what our psi t is. So now our capital psi, which was in terms of x and t, is equals to e to the power of negative I e t over h bar. Now, however, the right side instead, that we haven't put equals to anything, has to be solved as well. And we just said that the right side is the same thing as e. So we can say that the right side is equal to e. So let's multiply both sides by capital psi. We get, on the left side, we're going to get negative h bar squared over 2m, and then we're going to get psi, actually, well, yeah, we're going to get psi t, but just I'm not going to put it outside so it's clear for you to see. And then second derivative, or little psi over dx squared plus v capital psi is equals to e capital psi. Alright, so these two together, this one can be brought inside, doesn't matter, it's a constant, and so we get negative h bar over 2m times the second derivative of our capital psi is equals to dx squared, dx squared plus v capital psi is equals to e psi capital psi. Now, we can take the capital psi out on the left side, factor it out, we're going to get negative h bar squared over 2m, derivative squared in terms of x squared, plus the potential that multiplies capital psi is equals to e capital psi. Now, when we're multiplying this part over here, this one is the potential, and this part over here is the kinetic energy of the particle. So these two together, of course, equals the total energy. That's why we used E as a constant, not any other letter. So we know that also this part here is equals to the Hamiltonian, and it's going to be an operator, of course, because we don't have the function. So we can say that the Hamiltonian is equals to our energy, and the Hamiltonian of a function is going to be equal to the energy of that function, as you can see very quickly. Now we want to check, for example, what is the average value of the Hamiltonian? Hamiltonian or x. Okay, well, what is the average value of the sum of these two? Well, it's always going to be a constant, because we know that E dot is equals to 0 with no external forces, and we're measuring no external forces, and therefore the average will be equals to any value over simply the total, right? Well, let's prove it. So we're gonna have this, and we can just say that it's gonna be the integral of our function. Actually, no, let's do longer way for now. Okay. So this is going to be the integral from negative infinity to positive infinity of our psi, and then this is complex conjugate, and then h hat, and then our normal psi dx. Now we can take the psi out because this is constant, and then we'll have the integral from negative infinity to infinity. Well, we have these two left together, so we can just multiply them together and say it's the absolute value over psi squared dx. And we know that this part over here, is equals to 1 because of the normalization. And this part over here is equals to the total energy, because we just proved it earlier right here. So we're going to have E times 1, or simply E. And as you can see, it makes sense both mathematically and theoretically, logically. One more thing that we can think of is the h hat, the h operator, can be rewritten as p squared, or the momentum squared, over 2m plus v. V of x, of course. Now, why is this? Well, if you remember what our p is, we can just simply plug it into our operator, that is h, and we get the same thing, because we said p is equals to ih bar, I believe it's negative ih bar, ih bar, and then the derivative over x. So if we square this, p squared is equals to negative h bar, and then the second derivative in terms of x squared. As you can see, we can plug it in our h operator, and we get it back to our original function, that is this one over here. So negative h squared over 2m, second derivative of x squared, and of course the vx remains, it goes from there, so v. And that is the solution to our problem. Then the book talks about how you can prove that the solution is a linear combination of all the variable solutions, but that's a little bit too long for this video, so I'm going to stop here and talk about it next.